Most enterprise artificial intelligence systems today operate purely as orchestration shells. They sit on top of files, logs, and notes, acting as a conversational interface. Operationally, these are large language model read layers. They execute semantic searches across static text databases to summarize what an organization has already written. This creates a structural limitation. Standard retrieval systems store what you knew at a specific moment. It fails to capture the conditions under which you made a decision, the alternative options you discarded, and the empirical data of what happened next. Moving past this bottleneck requires abandoning pure text retrieval. The system must evolve into an abductive reasoning substrate, a framework that infers the most likely explanations and future states based on historical decision patterns. To power this substrate, the architecture requires a latent world model, integrating the Joint Embedding Predictive Architecture, or JEPA, proposed by AI researcher Jan LeCun. JEPA is a model design that learns to predict abstract representations of future states, rather than attempting to reconstruct exact pixels or text. A standard read layer can only echo past documents. Integrating a JEPA-powered substrate allows a system to execute zero-shot planning, adapting to entirely new scenarios, because it maps how humans navigate trade-offs. This brings us to the core mechanism of the architecture. Instead of indexing keywords, the system maps historical human choices into a high-dimensional mathematical space known as decision geometry. This diagram illustrates how information ceases to be a flat spreadsheet. It transforms into a geographical state space, a continuous, measurable terrain where past actions form specific coordinates. By tracing these coordinates over time, the system maps trajectories. This allows the model to predict multiple plausible future arcs based on proximity to past decisions, avoiding the error of deterministically hallucinating a single, rigid outcome. However, if an artificial intelligence uses these predictions to continuously rewrite its own internal logic, it risks logical drift. The system's baseline rules can slowly detach from the human user's actual intentions. To maintain structural coherence, the architecture enforces strict database-level transaction protocols directly on its own firmware. The model cannot alter its core logic without passing through a serialized, auditable commit process. Fusing this geometric state space with rigid transaction rules yields an anticipatory intelligence. The system projects probable futures while ensuring the human operator's parameters remain the strict, unaltered anchor of the narrative. The foundation of this geometry relies on replacing the standard text note with a distinctly different data structure, the immutable decision receipt. A traditional note captures a passing thought or observation. A decision receipt acts as a cryptographic log. It records a specific action taken, the environmental constraints present at that moment, and the eventual outcome. This diagram demonstrates how every receipt encodes a strict schema. It isolates the context of the problem, the multiple options the user considered, the specific bet they placed, and the resulting empirical data. Because these fields are standardized, individual receipts aggregate mathematically. They are translated into numerical vectors, establishing the coordinate system of our state space. In this geometry, choices with similar contexts and constraints naturally cluster together into distinct geographic regions, entirely independent of manual human tagging. When connected chronologically, these clustered decisions form measurable, causal trajectories. The system physically traces the route from an initial constraint to a final verified outcome. Text strings are highly vulnerable to ambiguity. Modeling human behavior strictly as immutable geometric vectors provides the mathematical rigor required for any system attempting to accurately forecast human outcomes. Standard generative models process a prompt and output a single deterministic string of text, hallucinating one fixed path forward. This geometric approach operates using an entirely different mechanism. The JEPA-powered world model does not train on raw internet text. It trains exclusively on the historical receipt graph, the actual log decisions and outcomes of the user. The model extracts patterns from these past decisions by utilizing self-supervised contrastive loss. Contrastive loss is a machine learning technique where a model learns to distinguish between similar and dissimilar data points to build robust representations without requiring manual data labels. This diagram shows how the encoder maps current data into abstract representations. It then projects multiple latent future states, represented as probability zones, rather than forcing a single definitive outcome. This topology allows the system to perform gradient descent. It analyzes the state space to identify local slopes where historical coherence and actual user outcomes mathematically improved over time. The model utilizes these gradients to suggest small, incremental actions that align with the user's established behavioral patterns. It avoids attempting to maximize arbitrary key performance indicators that ignore human context. Generating abstract latent regions instead of rigid text predictions allows the AI to offer flexible narrative prompts. The user retains full agency to accept, reject, or remix the suggested trajectory. All complex systems naturally drift toward entropy. In artificial intelligence, this entropy frequently manifests as hallucinations, answers that possess high linguistic coherence but lack any receipt-backed justification. A secondary form of entropy is biased operator weighting. This occurs when a model over-indexes on the user's preferences, generating overly confident outputs that merely mirror prior beliefs, a failure mode commonly identified as user flattery. This diagram maps how the architecture embeds structural countermeasures known as adversarial operators. These components actively interrogate and penalize flattering or unverified outputs before they reach the user. The primary node runs logical inversions, cross-references historical base rates, and strictly demands receipt-backed justification. If the data cannot be verified, the output's confidence score is aggressively downgraded. The system also implements a cognitive stop-loss mechanism. This protocol strictly gates access to high compute forecasting tools based entirely on the measured fidelity of the underlying data. If the input data is brittle, the system locks out massive multipath simulations. Operators must manually pass epistemic literacy gates, proving they understand confidence intervals and data quality before the system allocates intensive computing resources. Structurally penalizing unearned flattery and gating compute resources forces the model to prioritize rigorous epistemic accuracy over immediate user gratification. This situation introduces a deep architectural dilemma. When a self-modifying intelligence needs to update its own behavioral rules, how does it execute that change without splitting the system's logic into conflicting realities? Without strict controls, the architecture is vulnerable to multiverse drift. One subsystem might treat a new predictive rule as verified production code, while another subsystem simultaneously treats it as a quarantined experiment. To manage this risk, reversible local experiments are classified as two-way doors. These allow for rapid, isolated branching and cheap computation because the changes can be undone with minimal friction. Irreversible updates, such as modifications to the system's core schema, ethical guardrails, or primary operating canon, are classified as one-way doors. This diagram illustrates how the system applies strict database transaction logic to one-way doors, utilizing write-lock global serializability. Global serializability is a data all concurrent transactions execute in a sequence that leaves the entire system in a consistent, unified state. During this write-lock state, the system halts all other conflicting mutations. It runs intensive adversarial checks and simulations to ensure the proposed change does not corrupt existing data, resulting in a single globally agreed-upon commit. Once committed, the lock releases. Every isolated subsystem, language model shell, and predictive world model is immediately forced to read from and operate on the exact same updated epistemic firmware. Applying rigid transaction guarantees to abstract epistemic rules prevents a highly advanced self-updating intelligence from deteriorating into logically inconsistent hallucinations. The resulting architecture is entirely fractal. The structural logic remains identical whether evaluating a localized atomic task or mapping a large-scale organization-wide ecosystem. The exact same mathematical primitives utilized to evaluate a single career decision are the identical atoms that govern and serialize the operating system's global firmware updates. To make this high-dimensional space navigable, the system compresses the complexity into a Socratic interface known as the IDEA macro, standing for ingest, diagnose, envision, and act. While the underlying world model constantly computes geometric coordinates and gradient slopes, it surfaces those insights exclusively through this straightforward, human-readable questioning protocol. Translating advanced decision geometry into a simple macro allows users to effectively steer massive artificial intelligence parameters without requiring a background in tensor calculus. A single governing philosophy serves as the gravitational center holding this entire architecture together: notamation. Notamation is the strict design principle that all automation must permanently orbit the human narrative and explicit authorial intent, rather than displacing it. The architecture is physically barred from overriding human agency. It cannot alter foundational data or trajectories without the verified, receipt-backed intent of the operator. The network calculates an epistemically rigorous, globally serialized map of highly probable futures, but it refuses to take the steering wheel. By integrating predictive world models with uncompromising epistemic transaction guarantees, we construct an artificial intelligence that operates as a profound reasoning partner, leaving the human securely positioned as the undisputed author of their own trajectory.